Continuing on with the sample distribution of the sample mean, we're looking at section 7.3 is the sample distribution. So we've looked at what we mean by the error, what we mean by a sampling distribution. We figured out how to find mu or find the mean of the mean of the sample mean and the standard deviation of the sample mean. Now we're going to work with normally distributed value variables and see what we can do with this to actually get some numbers in here. Put it all together to get us ready for getting into, we're looking really at what's the error when we make these, use our descriptive statistics to do inferential statistics. So once we got this error stuff out of the way, we'll jump into that next chapter. So finish this up. So we have a variable is normally distributed with a mean of mu and a standard deviation of sigma. Then the sample size is of size n. So we take a sample from this variable that's normally distributed. The mean of my sample means is also normally distributed, and it has that mean of mu and a standard deviation of sigma over square root of n. And if we know mu and sigma and we know it's normally distributed, we can use our normal distribution to look at that and answer our questions. So that's kind of putting this all together. So if we look at, we talked about an earlier chapter, IQ is normally distributed, a mean of 100 and a standard deviation of 16. So if we do it a sample size of 4, what does it look like? A sample size of 16, what does it look like? So we're looking at the distribution of the sample means. So if n equals 4, again, mu equals mu, my mean is going to be 100. My standard deviation is 8. And we look down here. Here is the actual curve for my IQs. This is my curve of my samples of size 4. And if we plug in samples of size 16, we get this green one here. And you notice on all of these, well, the mean is always the same because we're saying the mean is the mean, right? But the mean is getting closer. They're clustering closer and closer together, which what it means is that if I make a sample of, with our regular distribution, if I pick a sample of 1, I'm all over the board. If I pick a sample of 4, my mean value of that, that I get of that sample is a better chance of being close to the actual mean. I get a sample of 16, I'm getting even closer. So here with a sample of 16, I'm pretty much between 90 and 110 on most of my samples. So I'm getting really close there. That says if I have that sample size of 16, I have a better chance of matching my actual population mean. And that's what we're looking at. The distributions are, the standard deviation is changing. I'm not finding anything else except the mean. So that's one thing. When we look at that, we're not really describing the whole distribution. We're just saying, I'm trying to figure out what's the mean of my population. And this is saying, hey, how close I can get to that actual mean is what this is showing us. So it works really well as I said, if the data is normally distributed, then the samples are going to be normally distributed. But one of the cool things is that if my sample size is large enough, we call relatively large. So it kind of depends on how large the population, how large is large, right? But if we're relatively large, X bar will still be normally distributed even if the data is not normally distributed. So that gets us to the central limit theorem, which is basically relatively large sample size. The variable x bar is approximately normally distributed. And again, always your approximation becomes better as your sample size increases. But we're going to take advantage of that because you don't always know if your actual population data is normally distributed because you don't have it all, right? So, to sum this up, you have some variable x, has a mean of mu, a standard deviation of sigma. For a sample size of n, we got mu is mu. Sigma of your sample means is the population standard deviation by the square root of n. If x is normally distributed, x bar is normally distributed. So it doesn't matter what sample size I pick. But if my sample size is large, I can still assume normal distribution of x bar. And large, we're going to say 30 or more. As long as we have at least 30 in our sample, we can use this approximation of use a normal distribution to approximate that, which is kind of nice. So when we look at this, putting this together, we're going to say birth weight of male babies has a standard deviation of about 1.33 pounds. So we're going to say if we take a sample of 400 males, what's the percentage of all of those possible samples I can pick of 400 male babies that will have the mean of my sample will be within 0.125 pounds of the the population mean. So in this case, I'm not telling you what the population mean is. We're using the sample to try to get some feeling for that. So let's take a look at this. Didn't say anything about the distribution of the population. I don't care. 400 is large. So we're going to assume normal distribution of x bar. So we can say mu is mu. Sigma of x bar. Now that changes, but we have the standard deviation of the population is 1.33 by the square root of 400 gives you 0.0665. Now, we're doing a normal distribution, so let's make it standard normal distribution because we got the table for that. So we'll turn those into z-scores. And look what happens when you do that. Your z-score, your weights are now going to be mu plus or minus or 1.125 because that's where we're looking for. We want to be within 0.125 of the actual population mean. So we take mu minus 0.125 minus mu, and the mu's cancel out. I get negative 0.125 is negative 1.818 or 1.88. It doesn't matter what the actual population mean is. My z-score, if I'm with lower than 0.125 of the mean, will be negative 1.88. If I'm more than 1.25 of the mean, it's positive 1.88. I don't need to know what that population mean actually was. Wow. Huh. Cool. Now, and since I'm dealing with the standard normal, I know that my mean is going to be 0. So again, I don't care what the mean is right now. I say with z-scores of negative 1.88 and 1.88, I look that up on my table. I get 0.9398. If I look at the graph here, that looks reasonable. About 93.98% of all samples of 400 male babies have a mean birth weight of 0.125 pounds of the population mean. That means that if you take a sample of 400 male babies, find the mean of that sample, you have about a 94% probability that your mean is going to be within 0.125 pounds of the actual population mean. So it's a reason, you can help you determine how reasonable would it be to to give that population mean based on your sample mean. That's kind of where we're trying to get at with this. So, as I say, I didn't need to know what that mean was when I did this. But this is saying I'm trying to use that sample mean to predict the population mean, and I got a 94% chance that I'm a pretty good prediction of it. Again, is it going to be exactly the population mean? Probably not. But we're within 0.125 pounds. So that kind of wraps up chapter 7. So have fun with your problems.